To enable reliable block manipulation, we first sampled HSV values for each color using a live camera feed and applied a k-means clustering algorithm to extract accurate color ranges. These HSV bounds were then used for real-time color segmentation, allowing the system to isolate blocks effectively. All blocks used for testing were sourced directly from the Rover kit, ensuring consistency. With the detection pipeline in place, the rover was able to identify and interact with blocks autonomously. In testing, the Leo rover successfully retrieved and stored at least three different colored blocks within the demonstration area. It consistently achieved a minimum detection rate of 85% when facing the target block, meeting the required specification for reliable performance. Here you can see how the RealSense detects only the colors that have been trained by the HSV tuner and the k-means clustering algorithm and disregards the colors and the obstacles that are not in the ranges provided by the tuner.
The technical requirement of the manipulator being able to place a target block into the bin was only partially completed. Although the manipulator does not place the block specifically into the bin, it is capable of placing the block down after picking it up as shown in the video, which could be adapted to pick up from the rear of the rover and place into the bin. This requirement wasn't fully completed as the prior logic to recognize when the rover reached the bin was not.
To ensure precise object handling, the Leo rover was configured to distinguish between desired targets and non-target obstacles. Using the color detection pipeline developed earlier, the software identifies only the colored block with the correct target color and classifies any other object regardless of shape or presence as an obstacle. In the demonstration shown, the Leo rover correctly detects the yellow block as the designated target while ignoring the nearby non-target object. As a result, the manipulator proceeds to interact only with the valid block, confirming the accurate classification and selective action.
The technical requirement of the manipulator being able to place a target block into the bin was only partially completed. Although the manipulator does not place the block specifically into the bin, it is capable of placing the block down after picking it up as shown in the video, which could be adapted to pick up from the rear of the rover and place into the bin. This requirement wasn't fully completed as the prior logic to recognize when the rover reached the bin was not completed yet. Contingencies for physical limitations such as the short length of the manipulator were managed in the final design as required by the technical requirements, by providing alternative mounting points for core components such as the depth camera, manipulator and block bucket. The video on screen shows how the bucket and camera can be moved if unexpected challenges mean additional space is required on the top or front of the rover. The final rover is also documented on the GitHub page to complete the requirement for contingency documentation. Size requirements for the custom rover components were adhered to by ensuring the payload sled remained within the boundaries of the rover. This was tested by inspecting the rover's 3D model, which matches the physical rover and clearly shows all components remaining within the footprint of the rover. As the components remain within the rover footprint, they also meet the 3 cm maximum oversize requirement. The second size technical requirement dictated that the payload sled had to be large enough to hold all sensor, manipulator and computation components. From visual inspection, it's clearly demonstrated that the payload sled can carry the required components without significant overhang. When taking into account the acceleration algorithm used in the rover, the viewing range of the rover, when combining the LiDAR and depth camera, provides a 270-degree viewing requirement. Component placement requirements were met by placing the sensor components as frontally as possible on the payload sled, whilst maintaining a sufficient viewing range. The LiDAR and depth camera were placed on separate levels to complete the component location requirement, whilst the manipulator was placed with minimal obstruction on the top of the rover. The manipulator has 360 degrees of horizontal rotational movement due to the clear upper level. The video shown demonstrates a separate component placement. The only part of these requirements not fully completed was the reach requirement of the manipulator, as the short length of the arm and its central placement restricts its reach. The mass requirements for the rover are satisfied as is visually shown to successfully carry the mass of a LiDAR, robotic arm, and Intel NUC with minimal payload sled warping.
While most of the design requirements were addressed, a few were only partially met. The final product did make use of 3D printed components manufactured only through university system as specified. However, not all hardware came from the Rover kit. Certain supporting elements such as mounts or structural fixtures were improvised for better integration or due to kit limitations. The Intel NUC and Rover systems were successfully powered by onboard battery, aligning with the requirement for independent operation. However, power stability under load was occasionally inconsistent during extended sessions, hence we used external power supplies plugged into the wall for long-term deployment. As for software, all custom developed programs were written in Python, ensuring compatibility with the onboard software. That said, a small portion of the peripheral or vision-related code reused from open source sources was originally developed in other languages and interfaced through Python bindings. Thus, while requirement was broadly satisfied, it wasn't really met in the strictest interpretation.
When a potential collision is detected, the LEO rover can stop moving within just 100 milliseconds. During the test at the lab, we set the LEO rover speed to zero point 0.1 meters per second to make sure the detection was accurate. Once the collision avoidance system kicks in, the rover stops immediately instead of gradually slowing down. This helps prevent any chance of it hitting an obstacle. We also set a safety limit so the rover will come to a stop no longer than 10 centimeters from an object. A smaller distance like 5 centimeters proved to be too risky because it sometimes led to collisions. Based on our test, the LEO rover successfully completed at least 9 out of every 10 tasks. In the successful runs, the LEO rover was able to explore the map and return to its starting point without any issues. Here is a short video showing the process. The LEO rover can successfully navigate through unknown environments without any preloaded map data. It's also able to map at least 80% of the surroundings around the LEO rover. In addition, the LEO rover can detect potential hazards in the environment within a range of 15 to 150 centimeters. Here's a short video showing how the LEO rover explores and builds a map.